Welcome back, everyone. So hopefully everyone is ready for day 2. So we're gonna go ahead and just get started. Our first session is about the SAR data access by Kang Wang. It's yours, Kang.
Yep. So, hey, thanks for coming back for the day 2. So we will start off with the kind of introduction to the data access. And this is partially based on the notes of Matt Wei's presentation in the last several years for this short course. So as shown in a similar plot that Xiaohua showed yesterday, there are many civilian satellite missions nowadays. This is of course outdated as you see, LISA was initially planned in the early 2020, but still pending for launch. But anyway, so the idea is that some of the data from some of the missions are open access, but some of the data are restricted. Here I outlined a few, for example, ERS, ERS2, and MSI. It is supposed to be restricted, but nowadays all those data are openly, freely open to everyone. You can download from InSAR, which I will mention a little bit. But for Sentinel missions, including Sentinel-1A, 1B, and 1C, data from those satellites are completely open, and everybody can get access to the data with no restrictions. For the open access data, there are a few archives, a few facilities from where you can get data from. You can get data. For example, the satellite Alaska Satellite Facility, it hosts a lot of SAR data from various missions, including Sentinel-1A, Sentinel-1B, and Sentinel-1C. ALOS missions from GMTSAR, as well as upcoming NISA data, which I will show a lab demo downloading or search and downloading data from this archive. And as I just mentioned, ERS and MSI data, ERS and MSI data are now open. Previously, you had to write a proposal to ask for data, but nowadays all those data can be accessed from InSAR. It's called on the fly service. And because Sentinel-1A and Sentinel-1 missions are European Space Agency missions, so they have their own archive. There's archive called Copernicus data space from where you can download data. And for the JAXA missions, including ALOS-1, ALOS-2, for those data you can download from a site called gPortal. The link is listed here. I won't show that, but you can check that out. Basically, all the ScanSAR mode data are now freely available to everyone. So including those open access data, there's also a few other sites I want to mention. One is called EarthScope SAR Archive, which what the data archive that EarthScope is hosting. So this is a kind of previously it's called WinSAR, Western United States InSAR consortium, but now it's this name has been deprecated, but still we still call it WinSAR it's still known as WinSAR for most of the community members. It hosts some data, including ERS-1, ERS-2, and MSI, but also some commercial satellite data that was purchased by UNESCO under the EarthScope program. And also we archive data, specific archive data from PIs. For example, if the data are restricted and the PI have access to those data, they can ask us to help archive those data. And also we have a user interface to search and download the data. So this is a GUI interface for the SAR. It's called SAR Archive. It basically searches the Earthscope SAR archive as well as the Alaska Satellite Facility archive. So in addition to the GUI interface, web interface, we also have a Python tool to automate the search and downloading. So the commands, basically, you can check out the codes here, but it's just to show that you can search by a lot of parameters, including the dates, the orbit number, and other parameters to restrict the search. So now I'm gonna show a lab demo to search the data from Alaska Satellite Facility. I think that's the place most of people will probably get data for this short course. You can simply open your browser and Google search ASF SAR data. The top one would be the site. So you want to click the vertex. Just to quickly go through a few options. Vertex is the web interface, and ASF search. This tab will lead you to an introduction of the API and also the Python tools that they have developed. But for the web interface, you want to click the vertex, and it will lead you here. By the way, I noticed that on ASF website says there was some intermittent network degradation. So I did notice that this morning. So just keep in mind if you experience something, this is probably expected, and just try it a couple minutes later. So from here, you can the options are that you can select the data sites for Sentinel-1. It's completely free. Everybody can get access to the data, but of course you have to register account and log in. So I have already logged in here, so you can see that it's already logged in. But once you log in, you can select the Sentinel-1 for the data set, and you can then zoom in to the map to where you want to get data for. This is kind of very probably very familiar to you guys. You have used the similar GIS interface. I'm gonna search the data over Southern California, for example. For this area, just drag a box here, and then I can filter the data by specifying, for example, the starting dates. Let's do from June 1st to maybe today, just basically to search the data in the last 1.5 months. And then for the file type, because Sentinel-1 data, when they deliver data, there are many data types. For InSAR, for GMT, especially for GMTSAR, you want to use the IL1 single look complex. That's the data you want to use for making interferograms. So I'm gonna choose IL1 here, and you can leave the beam mode as blank, but you can also choose IW. IW is the imaging mode for InSAR white swath. So direction, that's the field you can specify ascending or descending. We have discussed that yesterday. Some people ask what is descending and what is ascending. So basically you can select the flying direction. I'm gonna select descending. And now you can click the search. Hopefully it will pop up something very quickly. Yeah, it looks like there's something weird going on the website. Yeah, as I said, ASF site is experiencing some degradation in the network. I don't know if I can refresh the website. There's always a danger to do the live demo, but you get the idea. Basically, you can search, you can specify the time range, you can specify the area of interest, and also the flying direction, as well as the path number, or inside it's called orbit number, or actually track number. So you can specify you can basically filter the search by entering those fields. Once you are satisfying with those parameters, then you click the search. If the site is performing as expected, it will pop up something as shown here. So, for example, there are some boxes. There are some footprints for the saw images you can preview. But for us, if you have already specified the SLC as the data type, as the data type as I showed in the filter before, then you can just click the download, supposing that you have logged in. So I'm gonna try one thing here. I'm gonna click the download. Hopefully the download will initiate very soon. But you get the idea. So it will eventually download. Yeah, so that's the kind of the web interface. If you are once you are familiar with the workflow of the GMTSAR, you may want to kind of process a large data set if you want. Then you may want to automate the data downloading. ASF actually has developed a pretty nice software package. It's called ASF Search. It's a Python module you can incorporate in your own workflow. If you work with Python, basically you can search by all those parameters as I just showed on the web interface. You can check out the details, all the details here. So I'm gonna skip this part just to give you an idea that you can automate the data search and data downloading using the tools that they have developed. Of course, in the GMTSAR script that I have briefly showed, it also has the function to search the archive from ASF. Okay, so that was the data, but for all the InSAR processing, you also need the orbits. Someone from the class asked, do I need to install the orbit.tar when they install the software? Yeah, as Eric and I answered, if you only work with, for example, Sentinel-1, you don't need that because the orbit.tar are only needed for ERS and NVSAT data. For most of the modern missions, the orbit files come with the data. But for Sentinel-1, it's not. Sentinel-1 still need to download the data, the orbit file. How to download actually in GMTSAR, there was a command called download Sentinel-1 orbit.csh. It's pretty easy to use. Basically, you can just type in the command without any arguments. It will show you the basic usage of this script. So anyway, so you can try it out. The command name is called download Sentinel-1 orbit, and you can then once you have the image and the image file and the orbit file, you are ready to go for the data processing. I will stop sharing. That's pretty much what I have here, and I think Matt will show a tool of how to make an interferogram using the data you downloaded. Suppose you have successfully downloaded the data.
Great, thanks, Kang. And so we will have Matt to give a demonstration of the two-pass interferogram.
All right. Hello, everyone. I'm Matt Wei. Oh, can you hear me?
Yes.
Okay, good. Yeah, I'm Matt Wei. I'm on the faculty at the University of Rhode Island. I will show how to do this two-pass processing. All right, can you see my screen? And are you seeing the presenter mode or the?
Just a normal slides, no problem.
It's good. Okay. All right. All right. So just as a reminder, InSAR is an interferometry. Okay, so the basic physics is well understood, as shown in this Young's two-slit experiment. When you have a source, so these two slits like act as two equal source, and then when these electron microwave they interfere, they generate this interference pattern, right? And InSAR measure phase shift, not deformation directly. So what it does is every time it rotates, you collect one SAR image. Then when you have two, you compare the phase. Then you can convert the phase to deformation. All right. So it's another way to think about this is, okay, so for each SAR image, you have one amplitude and then one phase image, all right? So as showing on the left. Then sometime later, you get another SAR image. If you just look at amplitude and phase, they look, amplitude look over the same phase like random, right? But to do InSAR, you don't really need the amplitude image. You need these two phase image, then you calculate the phase difference, then you can get these beautiful colorful patterns, which are phase change, and then you convert the phase into line of sight deformation. All right, so that's a quick reminder. And when we talk about processing SAR images, you can do either like two-pass processing, which is you just pick two SAR images, you calculate interferograms, all right, an interferogram. Or you can have many images, then you calculate interferograms between many pairs, then you connect all the pairs, and then you develop a sort of a time series, InSAR time series. And Katya and Catherine will talk about the InSAR time series later. I will just do a demo for this very basic thing. You get two SAR images, you get an interferogram. And two-pass processing, so for events like earthquakes, volcanoes, and anything, or landslide, anything that create large deformation in a very short time period, if you just want to look at these deformation, all you need is just two SAR images, catch a difference, right? You don't really need time series. Okay. Let's do this. All right. So some basic, what do you need? All right. You need a computer with GMTSAR installed. Okay. It also needs to have FCDF and a GMT. If you look at the homework, I think there's instructions about this. And also you need data. You need two SAR images, which you can download from an ASF or the European sites or other places. And then you also need a digital elevation model, right? So these are what you need and how to do it, right? So first you have to set up the folders and the config file, which I will demonstrate in a second. And also you run this thing called a P2P underscore processing.csh. And this is there any? Wait a sec. Okay. Continue. All right, sorry. Then run this. Then after you run this C shell script, if everything goes well, then you can interpret the results. Then you need to just go to the folder and look at all the output files, and then you will see the results. All right. And I'll quickly explain the results. All right. So first, this demo, I did one for ALOS, which on the Haiti earthquake in 2010. Okay. So what I usually do is I will go to USGS earthquake catalog. I will search all these big earthquakes. And then this one, so I searched this one. I know where the epicenter approximately. Then I go to ASF, as Khan just demonstrated. You go there, you log in, all right? Then so in this particular case, I choose a point because I know earthquake is there, right? So I choose a point as a yellow point there. Then I choose ALOS, which is a set point, and also I specify a time window. Then these are the results. So for ALOS, for each image at ASF, you have different level of products on the right. And all you need is this level 1.0 file. Okay, so as highlighted in the red box. So you just download that. All right. And here I download two files. They're both in zip file. And then when you unzip them, these are the folders you'll get. So in each file folder, you get these 6 files, right? Then for InSAR processing, all you need is this one LED file, which is orbit, then the IMG file, which is image, right? So you just, these are the files you need. And also you need DEM. If you look at the homework, there are instructions. And basically there are two methods. Well, they're most likely like only one method. So GMT has a good tool that you can just use this command grd cut directly. You can download the DM. It's really useful and convenient. Just make sure you use this Earth relief 0.1 second model. Okay, so it's a 30-meter resolution, so it's the best you can get. If you don't specify the 0.1s, it will give you a very coarse model, which is not very useful for InSAR. All right. So the second method is there is a C shell script called make DM C shell. That's built in GMTSAR. If you install GMTSAR, you should have it. Then this is very similar. You give the range, longitude, latitude range, and then you choose mode. So the last letter 1 means it's 30-meter resolution, right? So for high latitudes, when your latitude beyond is bigger than 60 degrees, this method won't work because this uses SRTM. Then you need to use Aster DM. You can download Aster from their website. Just make sure you need to convert the format to GRD file if it's not already have that option. All right, so that's the next is configure file. You need to create this configure file. There is a C shell script called pop_config.csh. If you type that, you will have instructions of what kind of input you need. Then for this particular one, I need ALOS, so I just put ALOS. Then I save it to a file called config.alos.txt. And when you look at the text file, it's something like this. Start like this. All right. Okay. So by default, the configure file does not do face unwrap, right? So if you wanna want it to do face unwrap the first time, then all you need to do is go to that configure file and change a parameter called threshold_sniffle. Okay, so the default is 0. It's escape unwrapping. You can change it to something like 0.1. It's a good start point. All right. If you didn't do this, you just run your processing, then you find out it didn't do the unwrap. You can change the configure file. In addition to change the threshold sniffle, you can also change the proc stage, change it to number 5. Then when you rerun P2P processing, it will start from unwrapping stage. So it will not repeat the previous 4 steps. So that kind of saves time. All right. And you need to make sure Ghost script is installed in your system. So when I did it last week, I forgot. I started with a fresh copy of computer system where it didn't have Ghost script and it was not checked or automatically installed. So you need to have that. Or otherwise you'll have error like this one. All right. So when you run the processing script, this is the setup you need. Okay, you need a configure file. You need a folder called raw and have these 4 files. So 2 LED to IMG file. And then you have a separate folder called topo, which has dem.grd, which is your digital elevation model. All right. So when you have these 6 files set up like this, you can run this p2p underscore processing.csh, right? And the argument following that is saying, okay, we'll run ALOS, and here are the 2 image files we will processing, and then here is a configure file, right? So if there's anything wrong in the setup or the argument you gave, it will report error. And when you look at error message, you will understand like what you can sort of see what's going on. In most of the time, the error message is very useful. All right, so here is what I did when I run this. So on the top is a command, p2p processing ALOS, then image configure file. Then once you hit run, if your path, your like folder structure, everything is right, it will do like this. It will start processing these images. All right. All right. So once it's finished, assuming there's no error, you always need to check the output, make sure there's no error. Your folder should look like this. All right, there's 2 new folders called INTF and also SLC. To look at the results, you just go to the INTF, there's a subfolder. So the name of the subfolder tells you the sort of the date of the 2 SAR images. So in this case, it's 2009, day 59 of the year. So it's somewhere in February, late February. Then the second one is 2010, January 16th, right? So it's the 16th day of the year. And when you look into that folder, these are the files. You get all of the data file, some KML file, and some image files, either in PDF or PNG, okay? So the first thing I would recommend you to do, just look at the image files, because these are really the easy check and the results. And if you want to do any modeling with these deformation data, then you have to go through these GRD files, right? Okay, so here I showed sort of 7 images I created, and their names are below the images. So on the left, these face mask.pdf, these are images in radar coordinates, and you can see there the X and Y are range and azimuths. Then on the right, the 6 images have this name _LL, which means they are in latitude longitude. All right, so and the name of these files sort of indicated what they are. So there's phase field, unwrap, level site, correlation, display, okay, amplitude. All right, and these files are sort of more or less linked like this. All right, so when you have a phase in radar coordinates, you need to geocode it. That will convert it to latitude longitude, which is a phase mask LL. Then you filter it to reduce noise. That gives you the phase filter and also phase filter mask. Then you do phase unwrapping, which I think Molly will talk about it next. Then you have a continuous phase change. Then you convert that phase change to deformation, which is LOS, which is in like a centimeter units, I think, right? Then the correlation image really serve as a mask. So when the correlation is really low, we don't want these points, so we just mask it out. And it works well for water because water have 0 correlation, right? So these are the images. Okay, and there are also a lot of KML file. If you have Google Earth installed, you can just double click on KML, then it will open the image up on Google Earth, and it's really useful, especially if you want to really know where these things are, right? It's my favorite tool for looking at InSAR results. All right. Okay, just a few notes about different site plates. So the demo I just did was on ALOS. If you want to do Sentinel-1, you need to download orbit file independently. So there's two shell script you can use to download, depends on your operating system. And also because Sentinel has the data is much bigger than ALOS. Well, the demo I did is ALOS 1. I want to make it clear. Okay, so you need a machine with larger memory and a CPU. You don't want to do it on a laptop. It might take too long. All right. And also most Sentinel-1 data are in this TOPS mode. You know that by the name, if it has IW in the name, it means TOPS mode. It has three subswaps, IW1, 2, and 3. And you sort of treat these three as independent images, and you process them independently. All right. And because each swath is about 85 kilometers wide, it's pretty big. So a lot of times, if you're looking at earthquakes or volcanoes, you might just need to process one subswath. Okay. And for ERS and MVSAT, the orbit data are saved in this link, and it's in your homework instruction. Like when you install GMTSAR, you're supposed to install this. Okay. And this file needs to be saved at -usr-local-orbits. You have to use this path, otherwise GMTSAR won't be able to find the orbits, right? And next, I'll do a quick demo for the Sentinel-1. So I looked at earthquakes in 23. I found a bunch of them in Afghanistan in October 2023. So that's short on the left. These are magnitude 6.3 earthquakes. It's big enough to have deformations. All right. Then on the right, I go to SF again because I know exact location of these earthquakes. I just use a point as a area of interest. Then I just search at Sentinel-1 and set up the dates. Sometimes you get multiple image pop up. Then you just choose the one that covers most of the information, and then in these filters on the top right, sort of in the middle right of this ASF search, you can actually set up the path. So in that way, you can just you will see only images on that path. That's for make it easier to choose. And for Sentinel-1, all you need is this L1 SLC file that highlight on the red box. Okay, that's all the file you need, the only file you need. All right, so the setup is a little bit similar to ALOS, where you only need certain files. So for the case of Sentinel-1, you only need this VV polarization file. And then also you need this .tiff, which is the image file, and also the .xml, which is a notation file GMTSAR need. All right. So these are so here are two folders with two SAR images, and each have 6 files that you need. Also, you need to download the orbit files. It's this .eof file. Here I showed an example, like I put the two SAR image folder, the full path, into a file called list.txt, and then I give that to the download sentinel orbit.chl file. Then it will create, it actually will download the UF. When you have the UF, the name of the UF tells you the sort of the range of the orbit's data. So the two dates on near the end are the start and end of this orbit file. The first date is the date the file was created, I think. Okay, so in this way you know which orbits are for which SAR image, and that's important. Okay. All right. Then very similarly, when you set it up, again, you have to treat each subswath independently. So I create 3 folders, IW1, 2, 3, and in each you have the configure file, raw, and topo. In this case, the configure file you have to set up at TOPS, I think. Then in this raw there's two TIFF and two XML, right? They're all in VV polarization. They're all IW1. And then you save the orbit file too in the raw folder. Okay, here's a trick. Well, not trick. Here's something you need to do. So you cannot run like this directly. You also need to change the name of the EOF file. So here, what I did is I picked the first one is, let's see, 2023, October 7th to October 9th, right? So I know this one is for this October 8th image. So I changed that EOF file's name to exactly the same as the October 8th SAR image file name. Okay. So do the same for the other one. So after all these, you can start to run this P2P processing. It's the same for IW2. Okay, you set up the files and you change the UF name. All right. Then what you do, you just do it separately. If you want to process all the three subswaths. All right. So here is the results for this. This is a descending image which have three subswaths. And I only process IW1. It seems to cover the deformation area. And the red in the left image, these like a blob, these are the deformation caused by these earthquakes. So this InSAR image is from between October 8th to October 20th. And between this time, there are two earthquakes on the right. The focal magnetism are on the right. And so if you know what focal magnetism, you can sort of see what kind of faulting is this. So this is thrust faulting, and we are expecting uplift. So the red shows a decrease in line of sight phase. All right. Okay, I'll stop here. Thank you very much.
Thank you, Matt. And I think we're gonna go over one more lecture. Molly, how long is your lecture? Maybe we should take a 10 minutes break, then come back.
It'll probably be like 20 minutes-ish.
All right, so maybe we'll go over your lecture and then come back. Yeah.
That sounds good. All right. So I'm Molly. I'm going to talk a little bit about phase filtering and unwrapping. And many of these slides were prepared by Matt in previous years, so thank you for putting that together, Matt. So as a reminder, this has been said a couple times today, but InSAR measures phase shift, not deformation directly. So there are a few more calculations that we actually have to do before measuring how much the surface has moved up or down. So this figure here basically shows that if you have if the radar emits a signal, it'll go to the ground and come back to the satellite. My slides seem to be advancing for some reason. And the satellite will record some fraction of the wavelength as a measurement. Then at a second time, it'll emit another radar signal, and it'll receive that and record that fraction of the wavelength. So you can see the difference in phase is the actual measurement that we are making. So when you do this over a bunch of pixels next to each other or areas on the ground, we form these interferograms that you've now seen a bunch of times. And these all, if there is deformation, you'll see lots of these colorful fringes. So these include full cycles, in this case, from blue to white to yellow to red, back to blue. And then in this case, it'll have the jet color bar. So on the left here, we have a figure from the Ridgecrest earthquake, and you can see these fringes that emanate away from the fault line, which is seen here in black. And on the right, we have a figure over a volcano, and you can see the concentric circles right around the volcano. So here what we're seeing is what we call wrapped phase, and that's why you get these colorful fringes. So if we want to actually measure the absolute deformation, we have to do a step called unwrapping. So on the top here, you can see the Three Sisters volcanoes where we have those concentric fringes that range from, in this case, 0 to 2 pi, and they keep wrapping around the color bars. So after we unwrap, we'll actually get an image like the bottom here, and you can see that the color scale now will go from -130 to 30 millimeters. So this is computing the unwrapped change in phase. So another way to look at this is on the right here. This top circle, we have this wrapped phase that will oscillate between 0 and 2 pi. And that is because our radar measurements are only known, I think my slides must be on a timer or something because they keep advancing. InSAR phase is only known to modulo 2 pi, so we only know that fraction of the wavelength. So after we unwrap, we will basically be adding integer multiples of 2 pi to our measurements so we can get the absolute change in phase that you can see here on the bottom. So the algorithm that most InSAR workflows will use is this SNAFU algorithm, which stands for the statistical cost network flow algorithm for phase unwrapping. This is the paper here if anyone is interested in the more complicated details. But for some of this, the InSAR processing you're going to do here, you basically just need to know that GMTSAR will implement this algorithm for you. So this is a bit of a washed out figure, but on the left here, we have a wrapped interferogram, so you can see the really dense fringes. Here we have our correlation, which basically tells you how noisy your data are. So here pink is higher correlation and blue is lower correlation. And then after we unwrap, we get this unwrapped phase, which has fewer fringes. And you can see that the scale now goes from -20 to 20. And actually, you could make that scale larger and you wouldn't have any of these fringes here. So as I said, GMTSAR will do this for you. So you don't need to know too much about how the unwrapping actually works. But basically, you'll start with your wrapped interferogram, which is this phase.pdf or phase.grd, the data file. There are a couple things that will happen. You can mask it to get rid of some of the noisier pixels. So this is an example over the Salton Sea where we've gotten rid of the noisy pixels in the water. You can filter the image more to make it less noisy. And then we unwrap. And here you can see a change in the color bar, which indicates that this interferogram has now been unwrapped and we have our absolute phase values. From this unwrapped interferogram, you can convert it to the line of sight, which actually tells us how much the ground has moved either towards the satellite or away from the satellite. And then these are a couple of extra layers that are helpful in masking our interferograms. So unwrapping can be straightforward if you have smooth or spatially smooth phase like we do out here in the Salton Sea, where you can see the fringes pretty clearly. But when you have these noisy pixels in the actual water area, that creates a problem for snafu, and unwrapping can take a long time or sometimes fail. So there are other areas that are challenging for the unwrapping, and that would be any area with random phase. So if you have farmlands that are constantly tilled or irrigated, you'll have a noisier phase. It could be over steep terrain also. And any area that just changes a lot between your two SAR acquisitions will cause what we call temporal decorrelation, but essentially that will be noisy phase also that will be challenging to unwrap. So one thing we can do to actually reduce the amount of noise in our phase is we can filter our scenes or our interferograms. So on the left here, we have an unfiltered interferogram, and you can see this speckle, the noisy phase, but after we filter it, you can see that most of that noise is now gone. So that will make it easier to unwrap. So this is what it looks like in the phase. So hopefully you guys can tell that the interferogram on the right has a lot of this extra noise, but after we filter it, the phase is much smoother. So this one, probably both of these will unwrap all right, but the filtered one will be easier to unwrap. So another thing that will be helpful for your unwrapping is masking out any areas with really low coherence or areas with large bodies of water. So we can use our correlation layer. So it's core.grid. And you can look at it with NCView or the PDF, and you can see that the areas that are black have really low coherence and they will be harder to unwrap. But these areas in white should have your smooth, coherent phase. So what we can do is we can mask out these bodies of water so it doesn't try to unwrap all of the random noise in the Salton Sea. And then after we unwrap it, you can again see that we get this change in color bar and that our color bar will extend beyond the negative pi to pi radians. So there are cases where unwrapping can take a long time or may fail. And that's usually caused by these large bodies of water, like I mentioned before. So some of the things you can do to speed it up or prevent it from failing is either cutting out that body of water and just focusing on one area of your coherent phase, or you can change that correlation threshold to get rid of the noisy pixels. So in your config file, you can set this correlation threshold for snafu. I think it's 0.1 by default, but if you have an area that is struggling to unwrap, you can make this larger, and it will hopefully unwrap faster. And I believe there's also a threshold for the geocoding step down here, which will turn your interferogram from radar coordinates into geographic coordinates. So this is basically one of two parameters in the snafu.csh program that you can toggle. The next one is the unwrapping discontinuities. I think there was a question about this in the chat. Yeah, it's a maximum discontinuity. So if you have an area with an earthquake, say in Ridgecrest, you might want to change this defo max threshold to be 60 or 65, which will allow for a phase jump across your scene. So in an area with an earthquake, you might expect to have 60 cycles of deformation. So by default, SNAFU will try to compute a smooth continuous phase across your scene. But if you do know that there is an area like an earthquake with phase jump, then you'll want to set this defo max. So another thing you can toggle or set in the config file is your wavelength for your filter. So by default for Sentinel, the filter wavelength is 200 meters. So if you have pixels to begin with that are 5 by 15 meters, and then you multi-look them to say be 60-meter pixels, this filter wavelength will effectively choose a handful of pixels and smooth over them. So once you have unwrapped your interferogram, you will have your change in phase. That's unwrapped. And you can multiply that by lambda over 4 pi, and that will actually give you the line of sight displacement. So for Sentinel, the lambda will be 5.6 centimeters. So again, why is it 4 pi instead of 2 pi for this conversion? And that is because we are accounting for two-way travel time. So the signal goes from the radar to the ground and then back to the radar. So this is a wrapped interferogram on the left, and you can see the concentric fringes here. And then on the right, we have an unwrapped interferogram. So I want you to look carefully at the color bars and the scale. And there is a small problem with this unwrapped interferogram on the right. So I will give you a couple seconds to look at this, and then I'll tell you the answer. So what we can do on the left here is we can actually count the number of fringes. So let's say we're gonna start with this purple color. We can count about 1, 2, 3, 4, maybe 5 fringes in this earthquake region. So 5 fringes where one fringe is about 2.8 centimeters for Sentinel means you're going to have over 10 centimeters of line of sight displacement. And if we look here, we can see the color bar is on the millimeter scale. So we can do kind of a check on our interferogram if it was unwrapped correctly just by quickly counting the fringes in an area like this. So here we know that this scale actually needs to be centimeters, not millimeters. So just when you do unwrap, if it is obvious and you can count the fringes pretty easily, just a good idea to check and count to make sure that you're actually unwrapping correctly and you're not off by a factor of 10 like we are here. So just to summarize, we have to do phase unwrapping to convert that wrap phase from negative pi to pi into actual displacement measurements. And we can use the SNAFU algorithm to do that. And GMTSAR implements this for you. If you have clean, less noisy data, then the unwrapping is pretty simple. But if it's a little bit noisy, you can filter the data. And for areas that are completely decorrelated or really noisy, you may have to mask out large bodies of water or crop to an area where the signal is pretty coherent. So I think there's one more question in the chat earlier about when you use SNAFU and TERP over SNAFU. So the only difference between those two programs is that snafu and terp will do a nearest neighbor interpolation. So this is typically for large bodies of water. So you can try, if you have a place along the coast, you can try using snafu and terp instead of snafu, and it might unwrap faster or more correctly. But that might take a couple of tests. You might have to run both and then look at the outputs to see if it has worked properly. So I will stop there and leave any questions you may have in the chat.
Thank you, Molly. So let's take a 10 minutes break and come back in 10 minutes. Then Roger will talk about tropospheric noise. So for those of you who has question, please submit a QA. We are actively live answering them. And we'll put up a slide to show. I think we have a timer on the upper right corner for the break, for the 10 minutes break. So when it's done, I think there will be some music and then our session start.
How does that look? Can everyone see my slides all right?
Looks great.
Great. All right. So I'm going to be talking today about kind of what we refer to as the propagative error sources that confound InSAR signals. And what I mean by that are predominantly atmospheric artifacts as well as ionospheric artifacts. And if there's time, we'll touch a bit as well on methods that we can do to correct solid Earth tides as well. So, I want to start off by noting that the bulk of these notes were put together over several years by some of the names up here on these slides. So I want to thank everyone for doing all of the hard work and actually making these slides. I've just kind of tweaked them very minorly. So to lead off this discussion, I think it's helpful to think about these three kind of statements or questions that, as someone who's first starting to look at interferometry, you might find yourself asking. So let's say you've gone and generated the interferograms, like in the tutorial that we saw earlier today. You might now be wondering, all right, how do I actually go about and interpret it? How do I interpret these interferograms and make sure that what I'm seeing is actually what I expect to see? And what if you get an interferogram and you count the number of fringes like Molly was talking about, and it's a 6-day or a 12-day interferogram and you weren't expecting that much deformation in your area? What does that mean? And then if that is in fact due to something like an atmospheric error signal, is it possible for us to remove those noise terms to look at the underlying signal of interest? So we'll touch on a bit of these questions and hopefully give you a sense for the degree to which we can address some of these issues. So we'll start off though first with a little bit of a kind of mini quiz here, looking at a series of interferograms in Southern California. And the motivating question here is, well, where is the actual tectonic signal within these interferograms? Now, for context, we're looking at an area of the San Andreas Fault. And the San Andreas Fault, if assuming there's no large earthquake, exhibits about 30 to 40 millimeters of slip a year. So for context, one of these fringes on these interferograms is about 28 millimeters. So if we're looking at just a normal year with nothing too crazy going on, we might expect about a single fringe of deformation. And if we look now at, say, the 2-year interferogram here, we can see a few fringe cycles. So maybe some of that is geodetic in nature, but a lot of it seems to be like describing more than just what we'd expect for simple slip on a fault. If we look at this 24-day interferogram, we can see that there's a lot more going on now. We've got this kind of turbulent, ripply pattern. And this does not conform to what we might expect for a slip on a fault, particularly over only a 24-day period. Ditto for the 36-day interferogram. Now we're seeing a lot of complicated signals that seem to be correlated with the topography here. And so hold that thought. We'll talk about why that is. And then we look at another example of a 24-day interferogram. We don't see these turbulent patterns, but we do see some weird kind of decorrelation, perhaps. And then even on this 3-year interferogram, it is not telling us a really straightforward signal. So to cut to the chase, what we're looking at a lot of the time is the superposition of noise upon our signal of interest. That noise can be something that is related to the troposphere. It can be related to the topography of our scene. It can be related to the ionosphere. It can also be just simple temporal decorrelation like what Molly talked about. So how do we go about removing this noise? If we come back to thinking about what the fundamental interferometric measurement is that we are making, we are measuring that line of sight phase change here, which we can think about as this image of an interferogram. And that is composed of a bunch of other terms that are linearly added together that comprise this measured signal. Now, there's the true deformation, which is that signal of interest. If, for example, we're looking at a volcanic inflation event, but superimposed on that are things like orbital errors, topographic errors, tropospheric error, ionospheric error, solid Earth tides, and just simple thermal noise. And now I've color-coded these based on kind of how severe that noise is or the degree to which we can correct for it. And you'll see that some noise terms like orbital errors or topographic errors are mostly known and we can correct those. Our surface deformation is what we're interested in, and oftentimes we may not know what it looks like a priori. Our tropospheric noise is usually unknown as well and can follow a power law relationship, making it difficult to characterize, but we'll see some methods that we can perhaps exploit. And our ionospheric noise, while also unknown in practice, can often be measured if we are a little bit clever with some signal processing. And so we'll talk about ways in which that ionospheric noise can be mitigated. And so, for the purposes of this talk, we'll really be focusing on these 3 terms here, the troposphere, the ionosphere, and tidal noises. But it's important to know and keep in your mind everything that is going into the actual interferometric measurement, particularly when in practice, we're usually just interested in this true deformation signal. All right, so if we come now to the troposphere, what exactly is the troposphere when we refer to it in the context of InSAR? So the troposphere is the lowermost region in the atmosphere. It is the most water-dense area of the atmosphere, and it, from our purposes, is a nuisance because that variable water content is going to refract the radar waves as they pass through the troposphere, both on the way down to the surface and then on the way back up to the receiver. Now, the amount of that refraction is going to depend on atmospheric characteristics. So the pressure in the atmosphere or in the troposphere, the temperature, as well as the total amount of water vapor. All 3 of these characteristics are going to vary as a function of altitude. They're also going to vary laterally and temporally because our atmosphere is a turbulent and complex system. So atmospheric noise is generally unpredictable. The turbulent component is going to follow a power law in space and generally be uncorrelated in time. If there's a storm today, that doesn't mean necessarily that there's going to be a storm 12 days later when we image it again. Although there can be seasonal weather patterns, so you might sometimes see partial correlation in time. For example, if you're forming an interferometric pair between the rainy season in one year and another year. And we're often going to see some vertical layering that is correlated with topography, which we'll discuss in a few slides here. So the troposphere is kind of posing a lot of issues here in terms of noise because it has this complicated power law effect, and it also is uncorrelated in time. Generally, if we were to look at the atmosphere at a period of separation of, say, 5 minutes or so, those 2 observations are going to be correlated with each other. As we get to about 6 hours, which is the sampling for ECMWF, which is a climate reanalysis product, we can still have a pretty good structure function. But as we go to, say, 1 day or longer temporal spans, we really get an uncorrelated structure here. Now, if we look at a vertical profile in the troposphere, we'll see that there is a dependence on that refractivity as a function of altitude. This is what we call the dry component of the troposphere. But there's also this wet component, which is going to be dependent upon the amount of water vapor that's held by the troposphere at any point in time. And this is this can vary quite dramatically with time. So generally speaking, we can decompose the troposphere and the effect of atmosphere temperature and pressure on the index of refraction as falling into two major components, what we call the stratified component and the turbulent component. And I've represented these here with two kind of cartoon examples. So the stratified component here on the left is going to be associated with changes in path delay due to differences in elevation. So for example, if we look here at the top, we have a scene with a mountain in the middle. And let's say in our first image acquisition, there isn't a lot of stratification in the troposphere. It just has this constant gradation. That's not going to introduce any sort of systematic path delay as we look across the scene. However, if we now come and generate a second SAR image, say 12 days later, and let's say there's significant stratification in the troposphere, which we represent by this gradation here, there's now going to be a path delay or a phase delay associated with this scene because of the variable total path length through this stratified component. That's going to introduce a phase bias in our interferogram that is going to be correlated with this underlying topography. And we'll see in a second ways that we can maybe correct that. If we look at the turbulent component now, let's say in our first image, we have a nice, well-behaved troposphere. It's boring. There's not a whole lot going on. We're not going to expect any pronounced variation in path delay across this scene. But let's say our second image now just captures some storm events or some heterogeneities of water content represented by these two blobs here. We're now going to have path delays that are associated with these spatial structures. But again, these are not temporally correlated. And so that's going to introduce a complex superposition on top of our underlying signal of interest. So if we look first at the stratified tropospheric delay, we're going to show this again now and break this down into a series of animations here. We've got our stratification, and that's going to introduce this path delay here in pass 1. And then let's say in pass 2, that stratification isn't as pronounced. We see that our path delay, while having the same general trend, does not have as large of a magnitude. And that difference is now going to be introduced onto our interferogram. Now we can see an example of this in action. This is the Big Island of Hawaii. And on left, you can see the topography. You can see that there's quite a bit, about 4,000 meters of topographic relief across the Big Island. And if we look at two interferograms on the right here, you'll notice that there's pretty pronounced signals that correlate very well with this topography here. And so what we're seeing is this stratified tropospheric delay. Now, we're going to show some other examples here with that original interferogram that we saw earlier in California. And you'll notice that we've got these really tight fringes here in areas where we have high topographic relief. And so in practice, if we know the topography, which we generally do when we're doing our interferometric processing, we can perhaps correct for this stratified component. And so a pretty typical approach is to take our DEM at left here, to take our interferogram at right here, and you'll notice there's a pretty good correlation between these two. And we can just perform a simple linear regression where we regress our line of sight phase as a function of the elevation. And you'll see that it follows a pretty nice linear relationship. We can solve for this regression and then use that to empirically remove that stratified component from our interferogram. So great, that's one way that we can correct this stratified tropospheric delay. But what about the turbulent delay? Now, again, this is can be seen here if we have a first pass with no discernible structure, and then our second pass has some spatial variability in the troposphere, say due to higher tropospheric water content in these pockets. That's going to introduce this phase delay, which is going to have in some cases, complicated spatial structure, which might not be correlated at all with the underlying topography. So this phase delay is now uncorrelated in time. It's usually unpredictable, and we'll see what I mean by usually in a second. And it's going to follow a power law spectrum in space. If we look again at our interferograms in Southern California, you can see some examples of interferograms that have some component of a turbulent tropospheric delay superimposed on top of them. This image here on the bottom right is really a kind of a classic example of tropospheric delay whenever we see this kind of turbulent flow rippling pattern here. And you'll notice this has a characteristic spatial wavelength associated with it, but depending on the turbulence in the atmosphere, that spatial wavelength can vary in time. And so again, it is an unpredictable and complicated signal that we're dealing with here. And this is just showing again how these structures can follow power law distributions in both space and in time. So how might we deal with this? And we're looking again at this, turbulence example here. Well, one approach is to maybe notice that there's this characteristic length scale associated with our noise. And if we can characterize that length scale, and for example, if it's significantly different from the length scale of interest for our crustal deformation signal, then maybe we can apply some clever filtering and remove that tropospheric noise, leaving behind our signal of interest. And so if we're lucky and those length scales are sufficiently different, that is a plausible approach that we can take. But that's not a foolproof strategy. Our troposphere is not always going to be well behaved for us. And so these filtering approaches will only work in certain cases, not universally. So if we think more broadly about different atmospheric corrections, one option is to use weather models. These may not always have the needed accuracy or resolution, although we'll see some examples of this in a few slides. We can do filtering in both time or space, as I just mentioned, but if we don't perform our filtering correctly, we might be removing some of the real underlying signal of interest. And then, of course, there are these topography correlated models, these empirical models that are going to remove that stratified component. And we can see that that works pretty well. But if our deformation is also having some correlation with elevation, or if we're looking, for example, at, say, a volcanic inflation event, we might be, again, removing some of that signal. So generally speaking, it's good practice before you start kind of blindly applying some of these corrections to think about what your signal of interest is, what are those noise terms, how might they manifest, so that you can best remove these terms from your data. Now, if we think about some of these weather models here, this is just an example. You don't really need to look too closely at this equation here. The salient point here is that we can use weather models that will encode the humidity, the temperature, and the pressure in the atmosphere. And with these parameters, we can use a model function to derive an estimate of the refractive index of the troposphere at whatever time we acquire our SAR images. And if we have that refractive index at 2 times, we can solve for the expected phase delay due to the two-way travel in the troposphere. And from that, generate an estimate of what that line of sight phase error is. So this is an example using ERA5, a numerical weather model. There are other weather models that can be used for this approach. And you can see an example here with Sentinel-1 data where it actually works quite well. And so on the left is our interferogram. You can see that there is this kind of long wavelength signal as we move to the southeast in our scene. And if we look at the weather model, we'll see that that same signal is represented in the refractive index, or rather the difference in refractive index between those two scenes as we've acquired them. And so this is an example where that weather model correction is working very well. We can see another example. This is using the Gakos algorithm, which is going to use it's going to calculate that stratified delay as well as the turbulent delay. We're using GPS as well to help constrain the weather model. And in this case, we're doing pretty well again, but it's not perfect. There's still some residual issues. And generally, if you don't have GPS to help constrain your weather model, your reanalysis estimate can oftentimes be quite far off from the actual atmospheric structure. And so, oftentimes these corrections will not work in practice if your troposphere is sufficiently complicated. So I now want to turn to the ionosphere, which is another propagative error source, but it's quite different. The ionosphere, of course, is much higher up in altitude, and it is characterized by charged particles in the Earth's upper atmosphere. And what's happening now with the ionosphere is that these charged particles are going to introduce a vertical travel time change, or a line of sight travel change, that is proportional to the total electron content. In other words, if we integrate along the path that our radar signal is traveling, the total number of electrons in that path is going to cause a progressively larger phase shift. And it's also proportional to the wavelength squared, or inversely proportional to the frequency squared, meaning there's this wavelength dependence that we don't see in tropospheric error. So the ionosphere doesn't really affect X-band quite that badly, but as we go to higher wavelengths like L-band, it can be quite severe. Now, the ionosphere also varies. So it has kind of this 11-year solar cycle. And so, if you're looking at InSAR data in about 2020, that's great. Your sunspot number is pretty low. The ionosphere is not so fussy, but we're now kind of ramping up into another period of high ionospheric activity. And additionally, there is variation between day and night, as well as latitudinal variations in the ionosphere, all of which can make this signal complicated. So here's an example of an ionospheric phase ramp on ALOS 2 data. I think we might have seen this example previously yesterday. So we can see there's a large earthquake signals here, but they are just completely dominated by this ionospheric ramp here. Now, if we can remove this ramp and subtract it from our interferogram, we're left with a pretty good interferogram just encoding that crustal deformation signal. So how do we do this? Well, one way is to correct for the ionosphere using models of the total electron content. So these can often be generated by leveraging global networks of GNSS. And so here's an example of a tech model where we can see it's actually doing a pretty good job at capturing the ionospheric signal in this interferogram, and perhaps we can resolve this minor signal here. But oftentimes we don't have the necessary spatial resolution in these tech models for all applications. So another approach is to actually exploit this frequency dependence of the ionosphere. And this is actually what is used regularly in GNSS. And so the idea here is if we have two signals at different center frequencies, we can exploit the fact that they're going to experience different relative propagational delays and use that to solve for the variation in total electron content and therefore back out the phase delay that we'd expect. And so this is the relevant equation here. It depends on the difference in center frequency of the two signals we're doing, and it depends on the difference squared in the denominator. What this means is that any minor uncertainty here is going to be amplified based on the inverse difference of the frequencies. So for GNSS, those center frequencies are fairly small apart, so that noise amplification is only about 2.5. But if we look at something like Sentinel-1, for example, Here is our bandwidth, and we can separate it into a lower band and an upper band, each with different center frequencies. And that separation there is going to result in an amplification of 96.5. So if we have any minor errors in either one of these lower band solutions, that's going to blow up our noise and amplify it, which is not what we want. However, this method does work, and we can implement it to correct the ionosphere. Here's an example of using this split spectrum approach with ALOS2 data. ALOS2, because it's L-band, actually has a lesser noise amplification than Sentinel-1. And in fact, with the upcoming InSAR mission, this is the first mission explicitly designed with using this split spectrum technique. And this noise amplification problem is going to be much, much reduced because we'll have a split spectrum of 73 megahertz bandwidth. So once InSAR data starts getting collected, we will have regular corrections of the ionosphere built into the actual processing chain of that data, which is very exciting. So to summarize, when thinking about the ionosphere, there are two major methods of correction. There are models where we can solve for the total electron content. Generally, though, if we don't have enough spatial resolution, this can limit the performance of these models. We can also use split spectrum models, which ideally need a high bandwidth or an explicit dual frequency configuration, something like InSAR or existing GNSS stations to perform this split spectrum correction robustly. So I think just real quick, in the last 2 minutes, we can see that the troposphere and the ionosphere both can cause propagative errors in our interferograms, but there are ways to correct them, although I'll always issue the word of caution to make sure you understand the assumptions going into the corrections that you're using and have an idea of the noise that you expect in your interferograms before you start blindly applying corrections. Real quickly, in 1 minute or so, I'll just also mention that solid Earth tides are a signal that we can also now correct. And in fact, the GMTSAR processor has this built in now. This is an example of a solid Earth tide long wavelength ramp in Sentinel-1 data, again, in Southern California. You can see that this is a ramp of about, let's see, what is this, 30 millimeters or so. So large enough that it is something to consider. And the issue here is that we are getting this bias due to aliasing of these different tidal modes on our interferogram, which is going to depend on the temporal revisit of our satellite mission here. So if we're measuring tides every 2.7 days, it's going to appear as if it's varying once per 10 days, but this is an example of undersampling of our signal. And I'll really quickly say that there are many different tidal modes, each with different characteristic amplitudes and frequencies. And so depending on what mode you're considering, that will result in a different aliasing signal on different interferometric missions based on their repeat times. So, this is something that, depending on the tidal mode, if that amplitude is large enough that it is perhaps an issue, it's probably best to go ahead and correct it using some of the solid Earth tidal corrections that we now have in GMTSAR. And I will leave it at that just by saying that we now know these solid Earth tides to a pretty good accuracy, so we might as well correct them. And that's all I have. If you have any questions, feel free to throw them in the chat there, and I'll do my best to answer them.
Thank you, Roger. And our last session today is a joint session for batch processing and time series analysis. And usually, if you want to do a time series analysis, you have to process a stack of interferogram at a time. So we decided these two sessions should be joined. So Catherine Gons and Katia, it's yours now.
All right.
Hello.
Let me get these slides up.
Are you driving?
Happy to, unless you want to.
Whatever works.
I'm on it here.
Go for it.
Let me do this. Share screen. So hey everyone, my name's Catherine Guns, and I'm over at USGS, and Katya, do you want to introduce yourself?
My name is Katya Timofeeva. I am over at GPL. I am the discipline lead for the Solid Earth Science for the InSAR project science team. And yeah.
Excellent. Yeah. So we're doing sort of a tag team presentation today because these two topics are so intertwined together. And I'm going to start off talking a little bit about batch processing, and then we'll dive into time series. So the first thing that I'm going to cover here is just sort of why process time series at all, what's useful about it, why do we spend the time and energy trying to do it? And then we'll dive into some batch processing overview, and then I'll hand things over to Katya to talk about a little bit about time series networks and calculating time series. And then we'll switch back at the end to talk about a cool example of what to do with post-processing. So why process time series? What is time series? Why process it? So when we say time series, what I mean is we're talking about the processing of large volumes of SAR image data, meaning tens to hundreds to thousands of interferograms to calculate surface deformation over time. And so this is going from taking two SAR images, interfering them together to get a single interferogram, but doing that, many, many, many times over to get as much information about deformation as we can over time. And what this does is that it takes advantage of the substantial amount of open access data that's available to us, particularly with Sentinel-1 and will be with InSAR too, and allows us to take advantage of all that data. However, this has to come with a caveat that this can be really computationally expensive. So before you sort of dive into time series processing, you should make sure you have the computational power and resources to make that possible. So sort of why process time series, I get really excited about time series because this lets us estimate ground deformation as it varies in both time and space. So I have spent a long time working with GPS time series, but this is like GPS time series on steroids because we get a time series for every single pixel in an image of deformation. And so I'm going to run through just a couple examples here of why this is really cool. At the right, what you're seeing is some volcanic eruption activity at the Kilauea summit in the Big Island of Hawaii. And I apologize, the time series figure is a little small over here. But what this is showing is that there's deformation occurring in a single interferogram here at the left. But on the right, we're seeing time series. And time series over the time of between sort of January 2018 to November 2018. And each one of these points is a different pixel extracted at each one of these white circles here. And what this is showing is that in one area, there's sort of stable deformation over time, but in these bottom two pixels that are extracted right at the centers of deformation over here in this interferogram, there's a massive amount of deformation occurring. And this lets us see exactly what the rate of that deformation is over time and lets us understand what this volcanic system is doing. So as another example, what you're seeing here is vertical displacement rates or velocities from groundwater deformation. And so on the left, we're seeing groundwater deformation and vertical subsidence rates for the water year 2016. And this is in the southern San Joaquin Valley of California. So over here on the right is the Sierra Nevada mountains, and over here is the San Andreas Fault. And we got this big bullseye of deformation here, where it's actually these warmer colors are going down vertically. And on the right here, we can actually see how this has changed in the next water year, in water year 2017. And so the rates have changed pretty drastically because we actually had a lot of rain that year. And so being able to compare these different rates that we are able to extract from InSAR time series lets us understand these systems and how they're working out over time. As just a couple more examples, on the left, this is a similar sort of study where we are able to extract a velocity from an InSAR time series. But this velocity map not only tells us what the velocities are in these different sort of aquifer regions in the southern Bay Area here in California, but it's actually highlighted the presence of a fault that's running right through a major aquifer system. So we have different velocity rates on either side of this fault. And again, this lets us highlight what kind of deformation is occurring in space as well as in time. The other, just of course, amazing thing about time series is that we can extract InSAR time series and then compare it with other temporally varying data sets to better understand what that signal is doing and how we can better understand it with comparison to other kinds of data. And then lastly, sort of my bread and butter is looking at what we can do in post-processing to understand how we can extract parameter-like offsets from different time series. So what you're seeing here at the right is an InSAR time series in orange, and then a GNSS time series in blue for the Ridgecrest earthquake in 2019 in California. And what we're able to do here is extract actual offsets from each of these earthquakes, from this main earthquake in each of these different points of time series. And it also lets us look at cool things like post-seismic deformation, which varies in time and space as well. And so I hope just showing these few examples sort of convinces you that InSAR time series is a really powerful tool that is really useful in a number of different scenarios, in a number of different places, even in the world. So batch processing, I'm going to sort of guide us into batch processing and then turn things over to Katya. So when I say the word batch processing, really all I'm talking about is just processing many interferograms in one batch at one time. So instead of using something like PTP processing, we'll do a different sort of set of tools. And this is really useful anytime you want to process many interferograms in one go rather than a one-by-one approach. Often I use this for stacking multiple different interferograms to reduce the signal-to-noise ratio for surface deformation. And of course, this is critical when you want to process, thousands of interferograms for a time series, for example. And what this looks like in the way it's enabled for Sentinel-1 and other satellites in GMTSAR is that, like Matt was showing us, in a single interferogram, you'll generally use P2P processing. That's the main tool. It'll do sort of everything for you. You'll plug a config file into it. It'll all be set up. When you're processing in batch processing mode, though, you generally have to go step by step through the tools and the steps that are actually included in P2P processing for you. So it breaks everything up and you'll have to sort of execute it manually. What this does, though, is it gives you some flexibility about how to choose each one of those steps, and you can sort of tweak the tools as you need to. So for Sentinel-1 TOPS mode, you generally have these sort of steps here where you have pre-processing, you process your interferograms with iniftops.csh, you'll merge subswats if that's what you choose to do, and then you can unwrap. And then for other satellites, there's batch processing scripts for those as well. You can see we just sort of look at the tools without the TOPS mode definition there. And so these tools all exist in GMTSAR. There's many of them, and so it's sort of a wide open world for you to choose what you want to do, what data sets you want to work with. I'm more of a visual person, so I like to look at this in the form of, here are sort of the steps going left to right. And so this is a workflow overview for an example sort of Sentinel-1 system of time series and batch processing. And you would generally start with downloading your single look complex files, for example, from Alaska Satellite Facility, the Vertex website. And you can see in this sort of theoretical example, I've downloaded 3 different frames here for one file. But I want to stitch those together, and there's a tool to do that to make one large frame. And then once you have your stitched files together, then you can go to the next step where you have pre-processing happening. You co-register and align everything in that one step for all your different image files. And then once those are all aligned and co-registered, then you can calculate your interferograms. You can merge subswats if you want to. And then you go on to unwrapping and then applying any kind of corrections that you want to. And then after all that, once you get your unwrapped and or corrected interferograms, those get plugged into SBAS, or the actual time series processing software. And out pops an actual displacement time series with a velocity grid. So there's a lot of steps to this and a lot of sort of flexibility to do what you're interested in doing for your different projects. And so a critical question that I'm going to turn it over to Katya here is, with so many scenes, when you're processing in a big batch, how do you actually choose which interferogram pairs to process? And so turn it over to Katya.
Hi. So before I address the question of exactly which interferogram pairs you would choose and why, let's consider this little network. This is from the very early days of Sentinel-1. This is an example network of, or this is an example set of images. These are 16 images right here between 2015 and around the middle of 2016. So you have all these individual images, and what do you do with them? One question that may be on your mind after what Catherine has just introduced to us is, okay, why would you run the batch processing scripts? Why wouldn't you just run P2P every time? So there's an important distinction, and you can do that. You can, in fact, run P2P every time, except the problem then becomes that your interferograms are not going to be aligned perfectly. So the step of co-registering and aligning them beforehand to one single image is actually quite important. So the first thing you would have to do when you're looking at this network of images is to figure out which image you would like to be the one that is your reference, that you would like to align everything to. And in general, you could choose the one that is sort of in the middle of everything. So this plot shows time on the x-axis and perpendicular baseline on the y-axis. Oh, I'm moving my mouse. And of course you can't see it. Thank you, Catherine, for doing that. That's great. Yes. So basically, when you have a plot like this and you want to choose an image to which you would like to co-register everything, align all the different interferograms so that all your pixels are on top of each other, you would choose something that has sort of optimally in the middle range of baselines to make sure that your errors, exactly like that one, for example, that your errors are as small as possible during your co-registration. In general, for modern satellites like Sentinel, this doesn't matter quite as much as it used to because the baselines are already quite small, except for that one that you see outlier down on the bottom over there. Thank you. But in general, they are all, they should all be within a certain very, very tight space, very tight tube. And that's going to be true for also InSAR, hopefully someday also when we get ALOS-4 data and other future satellites that are in planning right now. So now that you've chosen your reference image or your master image, that one, what do you do with the rest of them? So interferograms are differences in images by definition. So which differences do you take? So you have quite a few options there. Go to next slide. One option is to just make sequential pairs. So you can just connect them like a connect the dots kind of game like this, and in time. And you can have the pairs that are sort of nearest neighbor to each other. This has a certain advantage. One advantage to this is that the interferograms then are very, very short, which means that they have much less of a chance of decorrelating in time. So the correlation is going to stay strong over time. The disadvantage, of course, is that, Roger just finished telling us about all this noise that can happen in interferograms, and it's huge. It's much, much bigger than the signal. These interferograms that are short tend to have much smaller signal to noise ratios. So if you're observing, if you have a really clever way of getting rid of the atmospheric, the tropospheric and ionospheric noise, or if you're observing signals that are moving very fast, so you expect large deformation signals over small time periods, or if for some reason you really care about temporal decorrelation, you're looking at a place where you have a lot of maybe vegetation for some missions that's very important, like Sentinel, maybe snow, and you want to look at places that tend to decorrelate very quickly. Short interferograms like this are the answer. That could be really good for you if you're looking at glaciers very fast, things like that. On the next slide, we have another option. You can make year-long pairs. So this is, a contrast to what we just saw. Basically, you can make your interferograms as long as possible. It could be specifically a year. For example, if you want to make sure, if you expect large seasonal signals in what you're looking at and you don't want those seasonal signals, you want to make sure that you have, you're observing the same thing in winter that you're going to be observing the next winter, same thing in the summer as you're going to be observing the next summer. If you want to sort of not look at anything that has to do with seasons, but really observe the deformation that happened over a certain period of time, year-long pairs are your friend. Again, long-term interferograms, whether it's a year or longer, they also have the advantage that you know, that when you're measuring small deformation signals, the signal to noise ratio is going to be much better than small interferograms. However, if you're looking at an area, in contrast to the previous example, if you're looking at an area where you have a lot of temporal decorrelation for whatever reason, whatever surface changes are going on there are causing that, you are probably going to lose your correlation in that in these year-long pairs. So it really depends on how you connect to your InSAR images to form interferograms. Really depends on what it is that you are trying to measure, and it's really worth thinking about when you plan out your processing. How about the next example? Of course, you have the opportunity to make all the possible connections. What this does is, well, it can give you as much information as possible about the different kinds of phase changes that you're observing in each scene. So, for example, as I'll talk about in a minute, for each of the different scenes, you have an atmospheric contribution that is the same for per date, per scene, not the same per interferogram. So if you want to know everything you can about something that just happened on one date, this is the complete network, like this is the answer. Dealing with many kinds of noise. I'm being really, really vague here because this is a topic that people are still exploring, whether this is a good idea or not. There are soil moisture changes that have been reported to affect interferograms individually, where to get rid of that noise, a complete network is necessary. This is an active area of research, so it may be possible that you may want to make all the interferograms. In general, I think the answer is somewhere in between. Making sequential pairs generally is just not enough. You don't get enough information. You're maybe, you know, if you just make sequential pairs in time, and only one of your interferograms is bad, suddenly your whole result can be affected by that one interferogram. So making some redundant pairs is generally a good idea. How many? It depends on your area, depends on what you're trying to measure, depends on your correlation. These are all things you should think about and plan, and keep in mind that if you do your processing and for some reason you get a bad result, it could be because of a network that you chose that may not be sufficient or maybe too much. So it is always helpful to take a look visually at your interferograms and understand what is going on in your imagery. Okay, we move forward. It was a really long explanation. Okay. Yes, so we can move on and look at some of the time series methods that exist. So the simplest thing you can do if you want to find out how much information has been happening over a long period of time is just stacking. So take a whole bunch of interferograms that you've created, whatever network it was, and just average them together. This is a very helpful first step, just to see. It's a minimal amount of calculation. You don't have to know anything that's under the hood. You can look into at your interferograms, you can look at an average, and it will tell you, it will get rid of some of the noise, especially some that's not temporally correlated, and it'll get you a mean rate over a certain time period. And of course, the longer time period you have, to some extent, the better results you will get. Of course, when the noise is correlated in time, it is harder to average out. We have seasonal patterns, it's harder to average them out. So this is one approach. It's just the simplest first step. It should take you a couple of minutes to do, and it's always helpful. The particular approach to, however, of course, is boring. So you don't get to you don't get to see what happens in time over time, as Catherine was pointing out in all those beautiful examples. So looking at time series is much more exciting, much more informative. And for time series, there exist a lot of different methods. So the one that we generally employ in GMTSAR is the SBAS method. It's still probably the most common method for time series estimation that exists today. even with a whole bunch of state-of-the-art technology that we now have and methods that we now have. SBAS is tried and true, and that's why we use it in GMTSAR. There's a test case available on the GMTSAR website that is really fun. Please download it and play with it. Another very popular approach is PS-InSAR and variations of it, persistent scatter InSAR. It is again, the most common software for that is still STAMPS, Stanford method for PS-InSAR. It was developed by Howard Zepker in Stanford. Wonderful method. It is, I think STAMPS still is in MATLAB, although I think there are Python versions that now exist. There are advantages to this method. It takes advantage of looking at the pixels that are most stable in an interferogram and in your imagery, and relying on those pixels to do your time series calculation. It is a lot more resource intensive than SBAS is in general, but it's something you could try. Giant, this last point is outdated. I think I kind of overlooked it. Giant still exists, but there are more newer software packages now. I would, instead of Giant, I guess the closest thing now is MintPy. So you can look into that as well. It's also based on SBAS, however, so it's very similar to what we do for GMTSAR. It has a lot of sort of built-in options and corrections that you can play around with. But again, I think we cover all those options and corrections in the SBAS version in GMTSAR as well. Okay, next slide, please. Right. So this is a general representation of how SBAS works. Basically, we set up a matrix inversion, and where you see the M matrix, that's what we want to recover. That's the incremental range change it says here. Incremental range change just means time series. These are the time series, incremental time series from day to day that you want to recover. The D matrix on the right is the displacements that you're getting just from your data, from your unwrapped interferograms, now that you've stack processed them and you've chosen the right ones and everything like that. And the most important, of course, is that matrix that has zeros and ones and all kinds of other information in them. And that represents the mapping between the time series that you are trying to recover, the M's, and the data that you put in. So the zeros and ones, so basically the first thing we do is we take a cube of data, as you see on the right. There's a stack of our unwrapped interferograms over time, and we extract the same pixel from all the stacks that we load into our inverse problem. And then we set up this matrix. And what this matrix does with the zeros and ones, it's basically a representation of time versus displacement. So the zeros and ones indicate, so the ones are for, there are ones in the slots of the time periods where, time steps, where a given interferogram shows you the deformation that happened, and zeros for the time period that the interferogram does not cover. So if you have a set of scenes, for example, one scene per month over a course of a year, you would have, and you have an interferogram that spans January to March, you would have a 1 in the January, February, and March slot, and zeros for the rest of the time. And then if you have others that span other months, you'd have zeros in the beginning and then ones for the time span. This is really not something you really have to know unless you want to write your own SBAS processing method. You should try it. It builds character. I think it's really fun to write your own SBAS processing method. But anyway, this is how it works. The important thing is that is those other things, all these other interesting characters that are in the design matrix there. And we could talk about them. I think the next slide explains a little bit, points at least to what they are. Okay, so right, so that was the explanation for the M's and the D's, but also on the bottom there where you have the negative and positive lambdas, those are weights, really fun weights that you can add to your inversion. And what we do in GMTSAR is we add these weights based on coherence. So for the same pixel in your stack of interferograms, for different interferograms, you will have a different value of coherence based on some changes that may have happened on the surface at the time, whether it's soil moisture, whether it's vegetation, agriculture, some sand dunes moving, anything, snow, you'll have changes in coherence. So generally, we can say that we probably trust the more coherent pixels more than we trust the less coherent pixels. They tend to have more noise associated with them when they're less coherent. So you can add weights based on that to your inversion. That's something that is built into the GMTSAR methods that we use. If you have any other information for any reason that you really trust based on how reliable different pixels are, you can also put that into this regularization. That again would require you to sort of either augment our method or write your own, but again, builds character, you can play around with it. And on the right, I think we're not pointing to them explicitly, but on the right, there are these sigma Bs on the right side of the design matrix. Those are perpendicular baselines. Again, this is less important now than it was years ago for satellites that used to have these really big baselines that jumped around all over the place. Nowadays, our new missions tend to be in a very narrow tube, but still, there may be some error that is based on that happens because of baseline error or a difference in where the satellite was for one of the passes as opposed to another pass. If your DEM is not perfect, if your digital elevation model is not perfect, you might get some error. So these sigma Bs are sort of kind of regularization based on the baseline. This is another option that we can use in GMTSAR available to us. So for the next slide, there is an example. It's quite an old example, but it's still quite good, from 2016 by Tong and Schmidt. And you could see a difference between doing traditional SPAS with no regularization on the right and doing coherence-based SPAS on the left. And there is a really pretty big difference. You can see that there's quite a bit less noise on the left when you weight your pixels based on the coherence. So it's really worth trying. Okay, and then the next slide. Basically, the way that the SPAS is set up in GMTSAR, if you run SPAS, the command, this is what you'll see. So your inputs are a list of interferograms that you're going to put in, a list of scenes that you're going to put in chronological order, please, that would be great. This explains some of the format that you should in which you should put in your scenes. You also need a number of interferogram, a number of SAR scenes, and you need to give it the dimension of the interferograms. By the way, this is true for every software that exists out there right now, for at least software that does SBAS for sure, like MinPy and others as well. Your interferograms should all be the same size. Otherwise it won't work. Again, it's true for everybody, not just us. So if you need to, if you're getting your interferograms from GMTSAR anyway, that was from batch processing at least, that will already be true. If you're not, then you may have to precondition them to be the same size and extent. And then you have some options. You can choose a smoothing factor, I believe in time. And you can choose an atmospheric correction and the number of interferograms that you used for the atmospheric correction, or 0 for a default to skip it. I'll tell you about the atmospheric correction in a moment. You can give the wavelength of the radar wave so that it can tell you what the displacement is in human readable format, not just radians. So you'll get meters or centimeters. And other information, your incidence angle, your range distance, your output RMS, and your DEM. So you could, outputs. It could also output your DEM error, that it will estimate from this inversion, and it could output the RMS of the data as well. So please do run through the example. Your output should look like a bunch of displacement grids that are cumulative time series, and a velocity grid that will give you the velocity over time. And in the next slide, or the following slide. So Roger already covered a lot of these. I'm only going to go through them rather quickly. So we have solid earth tides that are a problem. Ionosphere correction, that is a problem. And there are some unwrapping ambiguities that could be also a problem. This is something that that everyone, I think, is still working on. There are a number of possible atmospheric corrections that you can do. The tropospheric contribution can be a problem. And of course, there could be an earthquake in the middle of your time series, inconveniently, but maybe you don't care about the earthquake. So somehow you need to estimate and remove it so that you could look at everything else and it won't, it won't be a part of your time series. And that's something that Catherine is an expert in, I think. Yeah. So if we go to the next slide, we'll talk about each of these a little bit. So these are the most simple corrections you can apply. And the first things you could do, for example, is once you have your unwrapped interferogram, you can apply an atmospheric correction based on the elevation. Again, Roger already covered this, but basically you get rid of a lot of atmospheric noise that way. But there's also a danger that whatever's deforming might be deforming in a way that's correlated with topography as well. So you could be removing some of your deformation. That happens if you're looking at volcanoes. You don't want to do something like that. Another option that you could do is you could basically estimate what the GNSS velocities and time series are over your area of interest, where your interferogram is. You can interpolate between a whole bunch of GNSS stations, and then remove that to filter that and remove that from the interferogram. And in the end, you get something like what you have on the right. So you can compare the left version with the right version. It's corrected to a large extent. The downside, of course, to using a GNSS correction is that in some places you just don't have GNSS, and you can't really rely on it. But it can be very useful when you have a lot of GNSS points and when you really, really trust them. So next slide. Solid earth tides, we really covered that already. I don't want to go into it too much, but I just want to point out that there's a great paper by Shu and Samuel from 2020 where you can really read about the theory and methods for correcting it, and point out that it is becoming more important as we move into L-band and P-band missions. And if we go to the next slide, again, don't want to go into it too much, but the split spectrum method generally has been the way to go. NISAR in particular, and I will talk about NISAR tomorrow and how great NISAR is, but I would like to say that NISAR in particular will provide a layer as part of its products. It will provide a layer for the ionosphere correction for every interferogram. So you could just directly take that layer and use it to correct your interferograms. And yes, it is also true that NISAR has a subband that's designed for correcting the ionosphere, but also there will be several quite large areas on Earth. Again, I'll tell you about those later tomorrow, where NISAR will be getting observations both at S-band and L-band. That's an even bigger range of wavelengths that you could subtract and use to correct the ionosphere or learn something about the ionosphere. It's going to be quite exciting. Again, two important papers that you could read are by Fatahi et al. From 2017 and Liang et al. At 2018. I really highly recommend both of them. They're very informative. But moving on. So one of the ways that we can do atmospheric correction, of course, Roger covered the weather models and climate models that we could use to do this correction. In GMTSAR, we have a built-in function that does it a slightly different way. It is something like a filter that is somewhat adaptive in time. And yeah, this is on the right. There's an interferogram from ERS, I think. maybe ERS or NVSAT, I can't remember. But the point is that it's covering a space where there should be no deformation at all. And in fact, there's tons and tons of deformation. I think this is, I can't remember what time period this was. I think this was something on the order of 24 days or 30 days. And it's showing a deformation signal of plus or minus 2 centimeters where there shouldn't be any deformation. So clearly, this is atmosphere. Clearly, we have to find a way to filter it out. And if we move on to the next slide, the atmospheric correction that's available for the SPAS processing in GMTSAR is based on common scene stacking. It takes advantage of the fact that the interferograms that share common scene also have the same atmospheric contribution. So if you focus in on a certain scene, like the scene number 2 over there, you can then take interferograms with scenes on either side of it that are connected to it and subtract them from each other and get a really good estimate of the atmosphere. There's a secret step that we have after that, and I will tell you about that in a moment. But first, on the next slide, I want to prove to you first that it actually works. So we did this in the bad old days of ERS and NVSAT. So this is 2001 to 2010 combined data from ERS and NVSAT. And we are comparing our very irregular time series. There was irregular sampling in time and in space for these satellites. And yet, we were able to compute time series, and we're comparing them to GPS time series. We chose several points here close to LA, somewhere in the Mojave Desert, to do our tests. And you can see that our time series accurately recover the contributions, the deformation compared to GNSS, much better than uncorrected time series, which are shown as black dots on the plot. The red ones are corrected and the blue is GNSS. But not only that, we actually can see some of the really big, some of the bigger seasonal signals. So we do actually robustly recover a lot of time variation in this method. So if we go to the next slide, here's a secret step that I'm going to tell you about. So basically, you go through the entire catalog of interferograms. You go through all of your. This is one place where it's really good to make a network that is redundant. So it's not just sequential pairs, but has a lot of redundant interferograms. And you calculate your atmospheric contribution for each step. You end up with this whole big data set of what the atmosphere looks like on each date. And then the secret step is this. After you have this initial estimate, you basically you take all of these and you rank them based on which ones have the worst atmospheric contribution. At the following time you do this, you start with them. So you will start with the noisiest one. I think in this case it's probably this number 66 to the right in the middle of the image. And yeah, right there with the noisiest one, and calculate that one first, because now your signal is the atmosphere and the best signal to noise ratio is that one. Gonna be most reliably calculating that one. And then you're gonna move to the second noisiest one. I don't know which one it is, but your analysis will tell you, maybe 44. And you will calculate that one, but now you will use the atmosphere that you calculated from 66 to correct the interferograms that are connected to 44 before you do that. And you'll do that for each and every interferogram. And that's what our method does. One option that is included in the options for the SPAS script for GMTSAR is the number of connections you want to have, or the number of connections on either side that you want to have for calculating these atmospheric contributions. That's something for you to play around with. I would keep it to, I don't know, 3, a couple of months, not to make it too long. If you make it too long, you might smooth out some of the deformation signal inadvertently. Okay, and moving forward, I'm almost done and almost ready to hand it back to Catherine. This is from Xu et al. This is a very early example of sentinel processing. So on the top, you'll see a time series animation with the atmospheric correction on the bottom, we have it there without it. So you can see that the time series are definitely a lot cleaner when we correct for the atmosphere. And we have a very clear deformation signal. This is the Serra Prieto geothermal field. Looks very nice. Okay, thank you. And Catherine, take it away.
Right, thanks, Katya. Great. And so I'm taking over again to really show you an example of how you can apply time series and really time series post-processing to your InSAR time series. And so we're sort of entering a realm of active area of research. So this is something you can do if you want to pursue it down the line. But I think it's a cool example of what's possible. And so what you're seeing here in this slide is at the left, we're seeing 6 different displacement grids that come directly out of a time series processing. So each one represents a different epoch or a different timestamp. And what I've done in a cartoon sense is just extract this pixel in each one of these time grids and then plot it. So this is 1 pixel's time series. And this generally looks like, you can imagine, a single component of a GNSS time series. And so if we make this a more sort of recognizable sort of form of a time series model, what you're seeing here is a cartoon version of displacement over time, which are these blue stars. And then what I'm showing here is a potential hypothetical time series trajectory model that we can then fit to this hypothetical data set. And so this time series trajectory model includes all the sort of common terms you would use to fit this kind of displacement. So we have a slope, our overall trend, our velocity trend. We have a seasonal cycle signal term. We have a coseismic offset over here, and then we have a potential post-seismic decay. And all of these little separate terms get fit into a single model. And so this is what this looks like in reality. And for those of you that don't think about time series all that often, don't worry about the equation here. Think of this as each one of these terms representing a different kind of signal. And so what we've got here, we can sort of got an initial position for our time series, but then we have, again, the same thing, our interseismic velocity or this velocity slope trend. We have our annual seasonal and the semi-annual seasonal term, which is our sort of up and down seasonal signal represented visually down here. We have a coseismic offset. This will be for the 2019 Ridgecrest earthquake, which you'll see in a second, which is this little offset guy. And then over here, we have 2 post-seismic terms, which represent this post-seismic decay. So in this slide, you're seeing sort of the mathematical version up top and then a visual version of what those represent. And so we could do this for a single time series, which is great. But what we really want to do is repeat this for every single pixel in our time series. And so go do this a couple million times for all our different pixels. And we end up with something that can look like this. And so what you're seeing here is an estimate, a interseismic velocity trend estimate for the descending Sentinel-1 tracks in California. And so we've got Northern California over here on the left. This is kind of a sideways view of California. And then Southern California is over here on the right. And using this pixel by pixel time series trajectory model, we can get a really nice estimate of what is going on sort of statewide in all of these different descending tracks of data. And so I've labeled a bunch of different signals here, but I think that the coolest one that you can see right off the bat is that we've got San Andreas plate boundary motion right here. Everything in blue is moving away from the satellite, where the satellite's going down and looking this direction. And then everything in orange is essentially moving towards the satellite. You can sort of think of it like that. And then over here, we've got subsidence in the San Joaquin Valley, this big bullseye of deformation. There's a lot going on there, but all over the place, you can see a lot of really neat little signals. And this is what, again, sort of solving in this sense can help us do. But the other thing that time series trajectory modeling with an InSAR time series helps us do is solve for more specific deformation patterns that we're actually interested in understanding spatially and temporally. And so what you're seeing here are the coseismic estimates and the post-seismic estimate for the 2019 Ridgecrest earthquake, which happened over in Eastern California. And so this method really lets you solve for the coseismic offset for each one of those pixels time series and then plot it spatially. So you can see just how far that coseismic deformation has spread over the region and or just how far the post-seismic deformation has spread. And the neat thing about post-seismic then, which is sort of one of my pet projects, is how has that spatial pattern sort of changed with time and decayed away. over time, which is something you're able to do with InSAR time series in a way that you can't quite do with GNSS time series. So it's a really, really neat tool to let us visualize a lot of these different deformation mechanisms. And then one more thing we can do, of course, with any trajectory model that we apply to a time series, we can also solve for a root mean squared, or how well this model is fitting the data that we've provided it. And so in this particular scenario for descending track in California, the RMSs are pretty low, so mostly in the blue spectrum here. There's a couple areas where it gets a little high, mainly in the valley and up in the Sacramento Valley. And that shows us that really this model is actually doing a pretty good job at fitting all of these different pixels time series. There are, again, some areas for improvement, especially on the edges and in the valley. But just being able to estimate where's our model fitting well and where is it fitting poorly really helps us understand what we're trying to look at here. And then lastly, I wanted to put this note in about uncertainty in the time series, because uncertainties are really important. And as you've heard multiple times today and yesterday, there are a lot of different noise sources that can cause uncertainties, and especially high uncertainties with InSAR time series. And so, again, I think a lot about GNSS and InSAR. In GNSS processing, we have a pretty established way of estimating position error for each epoch of a time series, but we do not necessarily at this point have the same sort of strength and ability to do that in the InSAR, just because it's computationally expensive to do epoch by epoch uncertainties. We can estimate sort of a possible choice, that we can like come up with a way to see how the signal varies spatially around a given pixel. So for example, in this figure, in these figures that you're seeing here, particularly in this one right here, we have a GNSS mean time series in pink, and the actual GNSS time series are these gray dots behind the pink. And then InSAR time series are in blue, and you can see each one of these dots actually has an uncertainty bar on it, but that uncertainty bar is not coming from a covariance matrix, it's actually coming from a spatial standard deviation of how the pixels around that extracted pixel vary with their signal. And so it gives us a sense of, okay, how is this pixel related to the other pixels around it, and gives us a sense of how much that data is changing spatially, but it's not necessarily the true uncertainty, because it's a challenge. It's still an active area of research for determining those different uncertainties. But it's still really important to keep in mind that this is something we'd like to do and like to do better in the future. So estimating those epoch by epoch uncertainties is really important, and we'll get there someday, I hope. Yeah. But in this moment, estimating these and plotting them up is a tricky thing to do. So just to wrap up everything there, time series resources for GMTSAR, there's examples on the downloads page. We've referred to these a couple times now. There's actually a step-by-step recipe for Sentinel-1 time series on the GMTSAR website. And this literally goes step-by-step what command you have to enter into your terminal to do each one of these batch processing steps. And the data for this recipe is also available on the data downloads page. And then we also have in the documentation for GMTSAR, we have a batch processing guide that, again, will take you step by step and show you all the different tools that are necessary to get you started with time series processing. And of course, we're happy to answer any questions in the Q&A, and please email your instructors. We all, I think, have processed time series at one point or another. So if you're interested in this, please, reach out, and we're happy to answer any questions.
Thank you, Katia and Catherine. And I think this concludes today's session. Katia, there is one additional question for you in the Q&A, and we will have another session tomorrow. Before we end today's session, I also want to make a clarification that for this class, when you sign up for the class, there are two options. One is a planetary only, so which means you're going to be having this lecture materials and listen to the lectures. And also for the students who are signed up for the breakout session, we're going to have a homework set that kind of walks through the installation, interferogram generation, and so on. And so this is not required for student only sign up for the plenary only assignment, although later we're gonna make the homework available online because we have a good documentation that walk you through. So if you're interested, even without signing up the plenary, the breakout session, you should be able to have those material after the day 3 lectures, but that's not required. Those homework are only required for the student who sign up for the full session, including the breakout session. And so that concludes all the lecture today, and see you tomorrow.